Hi all. Today, Laplace's and Poisson's equation we will discuss in dielectrics and conductors. In earlier chapters, we discussed about electric field intensity E bar and D bar in a given space. By using Coulomb's law or Gauss law, we can calculate D bar or E bar. We can calculate D bar or E bar by using Coulomb's law or Gauss law. But in boundary conditions, Maxwell's equations, boundary condition to solve such problems for boundary conditions already we saw that what is boundary. When electric field is passing from one place to one medium to another medium, there exists a boundary condition. In such condition, the Gauss law or Coulomb's law we can't apply. To solve such numerical problems, Poisson's and Laplace's equations must be known. To solve that type of problems like boundary conditions, Poisson's and Laplace's equation must be required. Now we go for Laplace's and Poisson's equations. Practically, the charge and electric field intensity or potential V also can be calculated in some boundaries, that is in regions. From those values, it is necessary to obtain potential and E bar throughout the region. Such electrostatic problems are called boundary value problems. To solve these type of problems, Poisson's and Laplace's equations must be known. In this chapter, Poisson's and Laplace's equation we will discuss now. You know that Gauss law. What is Gauss law? The total charge enclosed in enclosed surface equal to total flux, that is psi equal to Q. That is Gauss law. We can say in point form the Gauss law. What is the point form of Gauss law? The point form of Gauss law is del dot D equal to rho V. The del dot D equal to rho V is the point form of Gauss law, where D bar is the flux density and rho V is volume charge density. Rho V is known as volume charge density. Del dot D equal to rho V. It is known that for a homogeneous and isotropic and nonlinear medium, we can relate D and E. D equal to epsilon E. You know the relation between D and epsilon E. For isotropic and linear medium, flux density and electric field intensity are directly proportional. Therefore, D equal to epsilon E. We can write. Make it as a Gauss law in point form is make it as equation 1. How to derive Poisson's equation? We are solving how to do Poisson's equation on Laplace's equations. For boundary conditions. For boundary conditions, we require Laplace's and Poisson's equations. This first we go for the Gauss law in point form is del dot D equal to rho V, where D bar you know that electric flux density and rho V is known as volume charge density. What is the relation for a linear medium? Flux density and electric field intensity both are related. D equal to epsilon E. Make it as equation number 2. Let us see, concentrate on this, how we are deriving Poisson's and Laplace's equations for boundary conditions to find potential V or E. Therefore, we can write D equal to epsilon E. You can substitute here in this equation. If you substitute in this equation 2, that is del dot D equal to epsilon E, we are substituting here. D equal to epsilon E, del dot E bar equal to rho V. You can understand this? Del dot D equal to rho V. From the Gauss law, in point form, we can write del dot D equal to rho V. It is a Gauss law. From the Gauss law, it is del dot epsilon E equal to rho V we can obtain. Make it as equation number 3. Make it as equation number 3. From the gradient relationship, what is potential gradient? From the gradient relationship, from the potential gradient, what is the relation between voltage and E bar? According to potential gradient or according to potential gradient, we can write E equal to minus del V. E equal to minus del V. potential gradient. In the previous classes we discussed this E bar equal to minus del V, where made as equation number 4. Okay, what are the equations we assumed? First, the Gauss law in point form is del dot D equal to rho V, and the relationship between D bar and E bar is D equal to epsilon E. The equation 2 we are substituting in equation 1, del dot epsilon E equal to rho V, that is the equation number 3. Assume that it is. Now according to gradient relationship, E equal to minus del V, make it as equation number 4. Substituting this equation 4 in equation 3, that is del dot epsilon E into, in place of E bar we can substitute minus del V we are substituted, that equal to rho V it is. Okay, simply the fourth equation is substituted in del dot epsilon E. The fourth equation, the gradient relationship, we are substituting in equation 3, that is del dot epsilon, you can write here, del dot epsilon into minus del V equal to rho V. Taking both sides we are multiplying, taking minus epsilon outside, we can write, how we can write? Taking minus epsilon outside, we can write, okay, that is by taking minus epsilon outside, because overall del dot del V equal to rho V. Simply we are taking outside minus epsilon. The equation 5 we can write like this. The equation 5 it is, assume that it is a equation 5, del dot epsilon, we can substitute here in this equation del dot epsilon E into minus del V. By taking minus epsilon outside, we can write del dot V, that equal to rho V, that is equation 5. The equation 5 we written minus epsilon del dot V equal to rho V. Now you can see the simple expression for Poisson's expression, we can see here. Therefore we can write, if you send this into this side, what will happen? It is will becomes divide del dot del V equal to minus rho V by epsilon. Now del dot del operation is called del square. Del dot del V, it is del square V, we can write del square V equal to minus rho V by epsilon. This equation 7, assume that it is a equation 7. The seventh equation is known as Poisson's equation. The seventh equation is known as Poisson's equation. Okay, how we are obtained del square V equal to minus rho V by epsilon? This equation we have to remember, del square V equal to minus rho V by epsilon is called Poisson's equation. In a certain region, volume charge density is 0. Assume that if the charge density is 0, rho V equal to 0, which is true for dielectric medium, then Poisson's equation takes, the equation is del square V equal to 0 for charge free region. If you consider dielectric cannot store the charge, the volume charge density is 0, it is true for dielectric medium, then the Poisson's equation can be written as del square V equal to 0 for charge free region it is. This equation is known as Poisson's equation. The Poisson's equation it is known as the Poisson's equation. In this special case of Poisson's equation and called Laplace's equation. ద లాప్లాసెస్ ఈక్వేషన్ ఎలా వస్తుందంటే దీని నుంచే స్పెషల్ కేస్ కన్సిడర్ చేస్తాం. ఇఫ్ ద రో v ఈక్వల్ టు 0 in the region, point charge or line charge or surface charge may be exist in singular locations. If the volume charge density is 0, ఇది Poisson's equation. ఈ Poisson's equationలో వాల్యూమ్ ఛార్జ్ డెన్సిటీ 0 అయిందంటే దీన్ని లాప్లాసియన్ అంటారు. ద లాప్లాసియన్ ఆఫ్ v, దట్ ఈస్ డెల్ స్క్వేర్ v is known as లాప్లాసియన్ ఆఫ్ v. Del square operation is known as Laplacian operation. Del square v or del square v is known as Laplacian of v. Hence we can say that it is known as Laplace's equation. Del square v equal to minus rho v by epsilon is the Poisson's equation. If the for ఒక ఛార్జ్లో వాల్యూమ్ ఛార్జ్ డెన్సిటీ 0 అయిందనుకోండి, అప్పుడు డెల్ స్క్వేర్ v ఈక్వల్ టు 0 అయిపోతుంది కదా. దీన్ని మనం ఏమంటామంటే Laplace's equation. The Laplacian of v equal to 0, that is known as Laplace's equation. Make it as equation number 7 and it is a equation number 8 and it is a equation number 8. The equation 7 is for homogeneous medium for which epsilon is constant. For which epsilon is constant, equation 7, it is equation 7 for which the medium, homogeneous medium where epsilon is constant, that is permittivity is constant. But if epsilon is not constant, then the medium is inhomogeneous medium. The equation 5 must be used as Poisson's equation. What is equation 5? The equation 5 must be used for a non-homogeneous medium, that is inhomogeneous medium. The equation 5 must be used as Poisson's equation for inhomogeneous medium. This equation will be used. Okay, let us see briefly how we obtained the Laplace's and Poisson's equation. The first one is Poisson's and Laplace's equation according to Gauss law in point form, because we know that simple Gauss law is psi equal to q, but according to Gauss law in point form del dot d equal to rho v, that is make it as equation 1. After that, the relation between d and d, epsilon e, d equal to epsilon e is the relation between d and e. Now we substituted equation 2 in equation 1, del dot epsilon a equal to rho v, that is make it as equation 3. According to, for a potential gradient formula, the potential gradient formula is E equal to minus del v, make it as equation number 4. Substitute the equation 4 in 3, we will get del dot, in place of E bar we can substitute d equal to epsilon e equal to minus del v, we are substituted here, minus del v, that equal to rho v, that is make it as equation number 5. After that, taking negative permittivity into one side, del dot del v is known as rho v, that is del dot del v equal to minus rho v by epsilon, or del square operation, the dot product of del dot del is del square v. What is del? The partial differentiation dou by dou x. What is the del v? Suppose del v, you can write del v as dou v by dou x ax plus ax is the unit vector, plus dou v by dou y plus dou v by dou z in all x y z direction. Del square v operation can be written as, we have to multiply this one, del square v, you can take del square v by dou square v by dou x plus ax also will be considered, ax dot ax is 1, we can neglect. Del square v equal to dou square v by dou x, we can write dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square, that equal to 0, that is known as Laplace's equation. Laplace's operation can be written as, this can be written as like this, dou square v by dou x plus dou v square by dou square v by dou y square plus dou square v by dou z square equal to 0, we can write. Del square v, how can you write? If you know del, the del dot del, the dot product of del, dou by dou x of dou v by dou x, plus dou by dou y of dou v by dou y. What if you multiply this dou by dou x into dou v by dou x, if you do again partial differentiation, what we will get? Del square dou square v by dou x square we will get. Dou square v by dou x square. This is about Laplacian of v. This is known as Laplacian of v. This is known as Laplacian of v, whereas this is known as Poisson's equations. Now we go for the potential v can be expressed in terms of three coordinate systems. Let us see that the potential, how we are explaining Cartesian coordinate system, how Laplace's equation in Cartesian form and Laplace's equation in different coordinate system, how can we write? Let us see that. The potential v can be expressed. Assume that v is the potential. V is the potential that can be expressed in xyz coordinate system v of xy, that is v of xyz. Or in case of cylindrical coordinate system, we can express v of r phi z. In spherical coordinate system, we can express v of r theta phi. V of r theta phi we can express. We can express like this in different coordinate systems, the v. Now, depending upon it, del square v operation for Laplace's equation. Del square v operation, how can we obtain? In Cartesian coordinate system, let us see. Del v equal to, what is the formula for del v? Dou v by dou x ax plus dou v by dou y ay plus dou v by dou z az. We can write like this, dou v. Now del dot del v, that is Laplace's equation is del dot del v equal to 0. That equal to del dot del v, del square v, it is known as del square v. That equal to, again we are doing partial differentiation of this one. That equal to dou by dou x of dou v by dou x, and we are substituting here dou v by dou x plus dou by dou y of dou v by dou y plus similarly dou by dou z of this one. Dou by dou z of this one. Here ax dot ax equal to becomes 1, hence we are not writing here. Ax dot product of unit vectors, ax dot ax is 1. Therefore, del square v equal to 0, that can be written as dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square equal to 0. The equation, assume that equation number 9. It is a equation number 9. Previously, what is equation number 8? Del square v equal to 0 is equation 8. Again we are written in Laplace's equation in Cartesian form. Cartesian coordinate systems, the Laplace's equation is del square v equal to dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. That make it as equation that equal to 0. This is the Laplace's equation in Cartesian form. In cylindrical form, let us see. In cylindrical form, del square v equal to, in cylindrical coordinate system, that is cylindrical, in cylindrical coordinate system, del square v equal to 1 by r dou by dou r of r dou v by dou r plus 1 by r square dou square v by dou phi square plus dou square v by dou z square equal to 0 plus dou square v by dou z square equal to 0. This is the equation, make it as equation 10. the Laplace's equation in cylindrical form. Similarly, we go for spherical coordinate system also. That is about Laplace's and Poisson's equation. If you want to calculate V in boundary conditions, potential gradient is not suitable, hence we go for Laplace's and Poisson's equation. To solve such a problems, that boundary conditions problem, in such electrostatic problems we are using this Laplace's and Poisson's equation. Okay, are you understand this? Poisson's and Laplace equation from the dot product. Hence we required first chapter is very important for basics for entire engineering electromagnetics. The dot product Gauss line point form. After that we related del square V equal to 0. That operation. Now del dot del V equal to minus rho V by epsilon. It is known as Poisson's equation. Del square V equal to minus rho V by epsilon is known as Poisson's equation. Del dot product. The dot product and the cross product all are important. Let us consider the potential gradient and the Laplace's equations. One example to understand. Verify the potential field. The potential field V equal to 4x square minus 6y square plus 2z square. It is 2z square. Verify the potential field is given below satisfies the Laplace's equation or not. The numerical problem, example problem is verify the potential field which is given by 4x square minus 6y square plus 2z square, whether it satisfies the Laplace's equation or not. How to verify? We already know that del square V equal to 0. Del square V equal to 0, that is Laplace's equation. Whether del operation on this equation, it satisfies as 0 or not, let us see. The equation V equal to 4x square minus 6y square plus 2z square. Now del square V, what is del square V? The partial differentiation square times, it is del square V can be written as dou square V by dou x square plus dou square V by dou z square plus dou square V by dou z square, dou y square, it is dou z square. We can write like this. Now we are applying this partial differentiation for this equation V. We are applying, that is dou square by dou x square into 4x square minus 6y square plus 2z square plus dou square by dou y square into this one plus dou square by dou z square into this one V. Okay, if you do partial differentiation dou by dou x of 4x square, that is 4x square, y square terms are 0, hence dou by, we can write dou by dou x into 4x square partial differentiation is 8x plus again we go for this dou square V by dou x of, first we are doing partial differentiation, after that we are doing again differentiation. Now we go for this one dou square V by dou y square we are doing. Dou square V by dou y square, how can you write dou by dou y of dou V by dou y, like that we can do. Hence dou by dou y of the partial differentiation of 4x square minus 6y square is minus 12y. This partial differentiation is minus 12y. Again we are doing differentiation of this, that equal to minus 12 we will get. And previously what we got in this 8x, if you do the differentiation again, this 8 will get, you can get 8, partial differentiation of 8 minus 12. Again we are doing dou v by dou z, this term becomes 0, this term becomes 0, this becomes 2z square, that is known as partial differentiation of that one is 4z, partial differentiation of that one is 4z. Again if you do the differentiation, 4 will come, that is 4 will come, you can see dou by dou z of 4z equal to 4. Therefore, del square v equal to 0. We are adding all this, that is 8 minus 12 plus 4, that equal to 0. We got del square v equal to 0. This way we can do, hence the potential field satisfies the Laplace's equation. Finally, del square v equal to 0. It is a simple problem. We can calculate d bar also by using Laplace's equations.